I'm extremely delighted to be here again, this time as a guest speaker, as opposed to students sitting there and listening to my great professors. And they were great, and I'm always grateful for the tools that they have equipped me with. Let's get down to business, and I would like you to ask me questions because the subject matter is so simple. I often I get embarrassed for even touching on it. So simple it is. So if anything passes by and you think it has an element which is not clear, any step which does not follow from the previous one, please stop me here. And we'll do it like we used to do in my time in the Technion. If you don't understand anything, you start moving your chair. You still do that? No? I go to UCLA and I talk and I talk and I talk, and at the end of my hour, they don't seem to understand what I said. I said, what's happening to you? And I remind them how we used to do it in the Technion. You can't move from one sentence to the other until everybody understands, or else the chairs will start moving. Anyhow, I hope you do to me what I used to do to my professors. Good. The topic is right here, and let's go right to the outline. I'm going to walk you through a personal story of how I got involved in this business of causal reasoning, starting from probabilistic reasoning. I started with probabilistic reasoning not because it is the natural way to do things, but because this is the way that education is structured. So I'll walk you through the transition from probabilistic reasoning to causal reasoning, and then from causes to counterfactuals. Two major transitions. Each of them is surrounded and accompanied by a traumatic experience on my side. And I see that it involves traumatic experience in the side of the people whom I'm trying to convince. Once we talk about those mental transitions, we'll go and talk about applications. And those will be divided into two parts. First is application in trying to equip machines with qualities or with languages that seems to be more natural for human conversation. And the second one is retooling the empirical sciences with what we learn from the first attempt. By attempting to equip machines with certain qualities, we learn about the way that people do it. And here I'm talking specifically about professionals in various fields like econometrics, like epidemiology, like in statistics, biostatistics. They have been coping with uncertainty for centuries and with cause-effect relation for centuries. And only now we understand what attempts were futile, what attempts lead someplace, what one has to assume in order to get the right results. So it has been formalized by what? By virtue of our aspiration to equip machine with such qualities. Here's my personal history. I read a paper by Rumelhart in 1976. He is a cognitive psychology of how children read text. I was inspired. I tried to emulate his ideas with machines in order to get the right sort of architecture and results in a probabilistic viewpoint. I got to the point where I noticed that trees give you no problem. Trees, I'll explain what I mean by trees. It's a structure of relationship among variables. Then we went to polytrees, and we got some nice results. And then came a period where people tried to emulate it or expand it into general graphs. And then I'll talk about the applications, and then the transition from beliefs to actions or to cause and effect. So let's start with Rumelhart. This is his 1976 paper where he wondered how children read text so fast and how they disambiguate words. Here, for instance, you have the word went, see, on the top sentence, and the same script, it turns into event on the second sentence, and children have no problem in continuing and reading and making the right interpretation. The idea is that the features of the letters help you disambiguate a word, and also the context of the sentence helps you disambiguate a word. So you have a handshaking here, top down and bottom up, and that's his picture from Rumelhart paper. So you have all kind of levels: semantic level, syntactic level, lexical level, down to the feature level, and all those sub-processes communicate with each other, and at the end of the communication process, here comes the interpretation, the car, as opposed to the cat. And when I looked at it, I said it must be done properly with probability theory proper. First, because I didn't know any other language. And if you're talking about uncertainty and disambiguating, so you have to deal with probability. That's what I was taught here in the Technion. So that could have been a narrow-mindedness, but could have been also a correct investment. And I say that this handshaking should be done right and should be done with no problem. Why there is a problem? Because if you have two variables, let's say smoke and fire, you get you smell smoke, so you increase the probability of that smoke has taken place, and that should feed back into fire, and you say, oh, there must be fire. And then the fire builds up belief, and there ought to be smoke. Then you have a positive feedback, and you have a build-up of belief based on no evidence. So that kind of thing you have to avoid when you have a top-down and bottom-up handshaking. Okay? And I knew that in probability it doesn't happen. Okay? You put down smoke and fire, and the right conditional probabilities, you have evidence for one, evidence for the other, you condition on both evidence, there's no positive feedback. Okay? So if you do things properly with probability, orthodox probability, you should get the right results. So that's what guided me. And I looked into the structure, and I picked up the easiest structure one can think of, or the tree. You encode into a tree a detective story, and then you have evidence of all kinds, like the body of a woman was found, a neighbor heard that the husband and the former husband had a loud discussion with the woman, and so on. I gave it the homework, and indeed, when you have a tree structure, then you can propagate belief from one variable to the other asynchronously, exactly like Rumelhart suggested that children reading comprehension take place. What I mean by asynchronously, it means that you have evidence here here in the periphery, right here. Somebody smells smoke. That propagates to the fire, propagates to a higher level. Maybe it's a summer night, and those transitions of belief, whether they're upgrading belief or downgrading belief, propagate through top to bottom until they are absorbed eventually in the peripheral nodes, and the network relaxes to what? To a stable equilibrium in which every variable receives the correct degree of belief. What do I mean by correct? That which you would compute on the basis of orthodox probability if you had the time and energy to encode the joint probability of all the variables and then condition it on the joint probability of all the evidence. Okay? That's orthodox. Okay? So that was a very exciting moment in my life when I noticed that asynchronous autonomous propagation can take place, belief propagation I called it. And then a student of mine came, broadened it to polytrees. These are structures in which you have two causes pointing to the same consequence. For instance, here you have earthquake and burglary. Both can result in the burglary alarm, in alarm sound, and a neighbor can call you, and if you find out that the radio announces earthquake, then this one cause achieves greater belief, which takes away belief in the other cause, because it was explained away. Okay? For this, you need a structure in which you have several causes pointing to the same consequence. Okay? And indeed, we also got a belief propagation in polytrees. That was great. And then this is how the belief propagation works. Each variable is assigned a processor. The processor communicates only with its neighbors and sends messages back and forth. Anytime, asynchrony, the processor can wake up in the middle of the night and say, oh, let me look at my neighbors. Oh, here's what I can do. And the neighbors likewise. Wake up whenever they want, send belief. Eventually, things get absorbed in the periphery, and every node gets the right orthodox probability. It's nice. So nice that I worked several years to try to generalize it to general graph. Because in general graph, you have loops going around. You have a common ancestor to several consequences, and they have also, they give rise to a grandchildren node. So how do we handle the loops? In 1985, I happened to stumble on a solution, which is if you have a common ancestor, then you condition on it. If you condition it, it looks like you are breaking the loop. If you condition it on a node, it's like forcing it to a constant. Forcing it to a constant, then you don't allow any flow of information. So you break the loop. Break the loop, you have a general system that gave me the courage of publishing a paper called Bayesian networks. Bayesian network right here, self-activated memory and so on. I used the name Bayesian because I needed to master all the credibility that I have, because at that time AI was immersed in an anti-Bayesian dispute. Or Bayesian analysis went into ill repute. The ruling paradigm was rule-based system. This is how you break the loop. You have a common ancestor, and you condition on it, and then you have what you have remaining is a tree where things propagate nicely, asynchronously, autonomously, and then you add up the various state of the conditioned common ancestor. Okay. However, what does it mean to break a loop? Now comes the theory. If you have a general theory for general graph, now you have to base it on some mathematics. And breaking the loop is an operation which is conditioning on. Yeah? It's based on conditioning on a node. Assuming that it is 0, assuming that it is 1. What does it mean to condition in a general graph? For that, we need the theory of general graph. So here it is a theory of Bayesian network in 2 slides. Okay? The construction is extremely simple. First, introduction. We're talking here about probability distribution being one object, well-defined mathematical object defined already in the time of Boole, if I'm not mistaken, or Kolmogorov, definitely. Okay? Then you have a graph, which is an object in the territory of computer science, if not mathematics. And you're trying to find relationship between the two. What could be the relationship? Well, one is a construction from one to the other is extremely simple, baby-like. If you have a joint probability, you can construct a graph by assuming any order, and then writing down the chain rule for probability theory, every variable giving its predecessors in the order. And then if you find a subset of the predecessors which is sufficient, then those subsets are proclaimed to be the parents of Mr. Xi in the graph. So given a distribution, you can build up, in an order, you can build up a graph simple, by this simple construction. No problem. And here's what you end up with for this particular graph, right? This is a probability distribution of 6 variables, can be broken down into a product of several conditional probabilities. And it works backward as well. If you take a product of these conditional probabilities, and you compute the conditional probability of x6 given x5, you find out you have exactly, you get back the number that you put here. So you have a consistency property. This is no problem. But the problem is deciding here, what are these judgments? What allows you to judge that a subset of variables is sufficient? It depends on a property called conditional independence. If you condition on a subset of variable, you don't need to look at all the rest. They are irrelevant. They are superfluous. Okay? And this is a qualitative judgment that you and I do when we construct that kind of network, conditional independence. And you have this orthogonal symbol for that. Xi is independent on all predecessors given the parents, the subset here. And I thought that this is the basis of human reasoning. If we have this ability to judge if certain things are irrelevant, okay, then we can break down conditional probability, huge mess of joint probability into islands which are loosely connected, loosely interacting, and we can do some processing. Okay? And indeed, whenever I ask a person, tell me, does the price of beans in China affect the traffic in Los Angeles? We said, no. Yeah. So we easily form consensus about things, whether things are relevant or irrelevant. If we easily find consensus, that means that we have some machinery in the mind that is responsible for that consensus, and it enables you to infer new irrelevancies from old irrelevancies. We have machinery for a logic of irrelevancies. Okay? And I thought at the time that this is the basis of human cognition. I was wrong, totally wrong. But let's go further. But still, once you believe that something is the basis, you got to exploit it and mathematize it. So what do we know about conditional independence? Or what else can we get from the graph? If you just replicate the judgments by which you constructed the graph, you haven't done a thing. You have to infer new things. What else can be inferred from those judgments? It turns out that there is a criterion called graph deseparation. Then it goes like that. Take any 3 subsets of variables in the graph to find out if subset X is independent on subset Y given subset Z. The criterion is, it is irrelevant whenever X is deseparated from Y by Z. What does that mean, deseparated? Let me explain to you in 2 sentences. You treat the graph as a plumbing network. And if you cut all the flows, all the paths that could pass information from one subset to the other, given the third, then the plumbing is stopped. Then you have a separation, and then the judgment of relevance is valid. Here is the plumbing trick. You have 2 kinds of valves, normal valves and abnormal valves. A node that emits an arrow is a normal valve. A collider in which 2 arrows collide is an abnormal valve. So now you have a system of pipes, and if you want to find out if x1 is independent on x6 given x5, find if there is a path which is blocked by those normal and abnormal valves. Very easy. If you want to exercise it, it's a good investment, because all of those that resist the temptation or resist my advice of not studying that are saving 5 minutes, but are losing years and years of hassle and difficulties in understanding themselves. I'll go as far as saying so. Okay, assuming that this valve processing is mastered by you and I. Okay? Now, anytime we want to find independence, we like look at the graph, look at the plumbing, and decide if one variable is irrelevant to another, given a third, using this plumbing. Good. Now, so the theorem goes that a path is Z separates on Z if and only if its valves are opened by Z. That allows you to build axiomatic theory for irrelevance, which was very important to prove the D-separation. So I should tell you that. How do you prove the D-separation? This is true. We tried for more than a year, and my former student Verma had tried with probability identities. He couldn't go anywhere. Once it was axiomatized using these axioms, the theorem came out smoothly and easily. So these are the axioms that conditional independence in probability theory obey. I wouldn't go through them, and I would convince you these are ways of deciding irrelevance from other irrelevance judgments. But the nice thing is that they share properties of graph separation. And that's what connects probability theory with graph. So now we have that ability, and the question is, what do we do about loops? In the 1985 to 1990s, there was a lot of activity on trying to find other algorithms, many algorithms that could equip general graph with the nice property that we have for trees and polytrees. And we had the algorithm based on conditioning, stochastic simulation, tree clustering, node elimination. I wouldn't bother you with that. And then there were problems in all of them. One problem was that it was proven that the time for all of them is exponential with a tree width. And the tree width is a graph property, which is the largest click if you try to cluster the graph into trees. And also, autonomy is lost. Autonomy is lost, I mean that somebody has to look. You should have a supervisor that look at the graph structure and say, oh, this is a common ancestor. So this guy is special. Let's do onto it something, a special operation that we don't do into others. And that breaks down the whole idea of autonomy. Every processor is identical to any other, and all the processor does is just communicate with the others. So two difficulties here. And it turns out that even in sparse networks, such as the grid, the tree width is extremely linear with the dimension of the picture, and the complexity is exponential. Okay. So you couldn't explain the speed at which children read. You couldn't explain the speed and the reliability with which we form consensus on the basis of such loop-breaking algorithms. It's exponential. So the ruling paradigm in AI is everything which is exponential cannot be done by people, and everything that can be done by people points to the possibility that things can be done in polynomial time. So something here can be done in polynomial time because we form consensus. Okay? So we go, and here I gave up, and I should say, in an act of desperation, I proposed it as a homework. I used the Talmudic trick that if you don't know the answer, you pose it as a question, and somebody eventually will find the answer. So I put it as a homework problem. Find out what happens when you ignore the fact that you have a loopy network. Assume that every processor thinks that he is a member of a polytree. There's no common ancestor. And they start passing messages under this make-believe hypothesis. And these messages circulate again and again. What will happen eventually? Do they converge? If they converge, do they converge to the right results? And so on and so on. It turns out that this turned out to be the straw that broke the camel's back. Everybody who tried it noticed that things converge beautifully to the right results, and the work of trying to find out why is still going on. We do not have a complete theory as to why things work so nicely in so many applications, but so many applications have benefited from that. And today, people are processing thousands and 10,000 of variables with that make-believe, belief propagation algorithm. And you have application going from, I just named 19 of them, from medical diagnosis to homeland security to genetic counseling and so on. If you want to add any area where you have uncertainty, you can model it with Bayesian network, energize the belief propagation. You get results which most of the time gives you the correct orthodox probability, and we don't know why. Okay. At this point, you can ask, okay, if you have so many applications and people are happy, why continue? That happened in the 1990s. And the reasons I'm continuing is because there's more to life than probability. And I'd like to spend a few words about the distinctions and the mental barriers of going from beliefs to causes. They go through effect of intervention, do calculus, I just mentioned by name, I wouldn't elaborate now. Then we'll have another transition from causes to counterfactual. Then we talk about the causal hierarchy. And then applications, and here I'll focus on 3 applications. Evaluation of policies, mediation analysis, and generalization, which will unveil the victory of counterfactual reasoning. This is statistics proper. This is how we learn statistics in Statistics 101. Back in the background, there is an oracle whom nobody has seen. Nobody has seen. But it's assumed to exist there. It's called a joint probability distribution. And that oracle spits samples on us, data, and our job is to find a certain property of the oracle, such as find the mean, for instance, estimate the mean, or the variance. These are all properties of a distribution. Give you a practical example. Many people are making good money for Google trying to find whether customers who bought product A would also buy product B. Simple example. A and B could be B could be a collection of variables, or an A could be other properties of the customers. And it's, you see, here's the property. It's a probability of B, buying B, given buying A. It's a property that you can express in terms of the oracle P. If you had P, you didn't have to go through the estimation. But we don't have P. Our oracle is hidden. And when he or she is gracious, it spits out samples. We look at the samples and we estimate the properties of the oracle. This is the total paradigm of statistics. And I said Q can be a very complex number. That's why you have shelves and shelves in the library of statistic books. But basically, this is what statistics is. Now, it's not the end, it's not the whole, this is not what people want to find out. If you are a pollster or a sales manager, yes, that's enough for you to predict what the customer behavior. But if you are dealing with intervention, like infer whether customers who bought A would buy product B if we double the price. So imagine that the sales manager of a given firm wakes up in the morning in a greedy mood. What if we double the price? The sales manager looks at the record of the company. They have records of price fluctuations, sales, and competitor behavior. And you look at the record and you say, what will happen if I double the price? Out of sheer greed. And that is not even a property of the joint distribution, because never before had price been raised to double its value today, and never before it was done regardless of other variables in the field, such as the competitor behavior and so on. So here is the dilemma of how even to express that query. Find the probability of B given A, but given that we do something, we double the price. Mathematically, it cannot even be expressed in terms of the property of the supposed joint distribution. It doesn't have a connective in proper probability theory to tell you what will happen if you intervene, because when you intervene, you change the probability distribution. And nothing in the axioms of Kolmogorov, it tells you how probability distribution changes if you change one parameter, nothing tells you how one parameter of a distribution change when you change the other. So what do? Let's now go one further. Let's now ask a more sophisticated question, which I call retrospection. Infer whether Joe, a specific customer, who bought product A, would have bought A had we doubled the price before. So we are talking here about a counterfactual, thinking back, inferring what the world would be like if a certain action would not have taken place. And that is the counterfactual, or retrospection, that I'm going to lead you to, because I believe this is the basis of scientific thinking, not the probability. So I'm leading you into a certain trap, and I'm warning you in advance. So what I exemplified so far was the three-level causal hierarchy. At the top level, you have associational, pure statistics, evidential reasoning. What if I see X? What can you tell me about the world if I see X? You have a symptom. I saw X. Okay? You're smiling to me. What can I infer? Then the second level is interventional. What if I do? What if I give you an aspirin and I force you to take it? I double the price. I lower interest rates. In every field you have. This is what people really pay statisticians to do. But statisticians give them that. And then comes the third level, retrospectional, counterfactual, or token. Philosophers call it token. What if I hadn't done something, which in actuality I did do? Okay? Should I suffer regret? And you can ask me, who cares about regret? But let's stick with the mathematics first. The nice thing about this level is that you cannot, they are loosely mixed. You cannot get a conclusion in layer I without some assumption in layer I or higher. So you have a very loose coupling between them. And which means that each one of them has a syntactic signature that identify in which level you are and what assumptions you need in order to get conclusion in that level. And the paradigm is going to shift totally now. Instead of assuming that a joint distribution is our oracle, the basis of our knowledge, the last word, the last expert whom we consult, we have another one. The true oracle, a data generating model, okay, of which a joint probability is just a surface phenomenon. Okay. And what is a data generating model? It's an invariant strategy. Some call it mechanism, some recipe, some laws of nature, some protocol, and counterfactual, by which nature assigns values to variables in the analysis. So you imagine that Lady Nature is responsible for everything we see here in the room. This table has a certain temperature. And this Temperature is assigned by the radiation from this bulb, by your breathing, other variables in the environment. Okay? And someplace there is in nature who takes all these variables and computes, and assigns 38 degrees centigrade. And that goes on for every variable. Okay? The height of my hair, everything goes on like that. That is the data generating math. It's a Laplacian conception of science. It's because we are talking about assigning value, not assigning probability. Heisenberg broke it, but it's assigning of deterministic assignment of values based on the values taken by other variables. And statisticians don't think that way. Statisticians think what experiment you need to do to verify one variable or another. Okay? We are thinking now in terms of nature and not in terms of experiment. Experiment is a crude way of finding out those relationships among the variables. And it's all, now I'm going to focus on that yellow and ask ourselves, why counterfactual? Who cares about how things would have been in a different scenario? Why not just be pragmatic? We want to find out what will happen if I kick this object or another. That's what matters, right? Well, this is not exactly how physics developed. Physics developed on the basis of counterfactual thinking, and I will convince you by going into the first physicist that I know in the Bible. It wasn't Adam, because if you remember, God asked Adam, did you eat from the tree of knowledge? He didn't ask him, why did you eat? He just asked for facts. The first statistician, the first scientist was Abraham. Because when God told Abraham what he is about to do to Sodom and Gomorrah and to destroy the city, Abraham said, hey, you can't do that. התספה צדיק גם רשע? השופט כל הארץ לא יעשה משפט? You can't smite the righteous with the wicked. It just ain't done. And are you going to destroy the city if you find there 50 righteous people? Now this is counterfactual. If there were 50 righteous people in the city, would you destroy it? And Abraham says, God says, no. If there were 50 righteous people, I ain't going to destroy it. I'm going to be satisfied. So Abraham said, what about 45? And God says, no, 45 is enough for me. I ain't going to destroy it. So Abraham said, are you going to destroy a city just on account of 5? And then he goes down to 40, to 30, to 20, to 10, and we all know what happened. But the question that we ask ourselves is, why is Abraham haggling about a world which doesn't exist? God knows how to count. Does Abraham doubt God's ability to count or to distinguish righteous from wicked and count them properly? So what's all this struggle about how many people there are? What is Abraham trying to verify? Abraham is trying to verify the general law for collective punishment. That's what Abraham is about. Not only Sodom and Gomorrah, but any city in the world, right? Under what condition would you punish the righteous on account of the wicked? Shachen Ra. And that is exactly the spirit of scientific exploration. We want to find the general law. And counterfactual is another way in which we express this desire to find the general law. What if things were differently? And indeed, the whole physics is built on the idea of a function. What is a function? Y, for every x, you have a y. Today we see x is equal to 0. But I give you the function, which means I give you the counterfactual, how y would assign a value, what the magnitude of y would be if x were different. That's the idea of the function. So it's Counterfactuals are extremely simple. They are nothing more than the theory of functions. You can say, but we haven't found counterfactual in physics. All we see is functions. Here it is. Take, for instance, Hooke's law. If you look at the physics book, all you find algebraic equations, right? No counterfactual. The name counterfactual will probably scare every physics teacher. It turns out that it's incorrect to look at physics as a collection of algebraic equations. It's not algebraic, and I'll prove it to you right now. Look at Hooke's law. It says that the length of a spring is equal to a constant, in our case 2, times the weight that you hang on it. Okay? So here is the equation for the spring. Here you hang on it 1 kilogram. So x is equal to 1. And find a solution. The solution is x is equal to 1, y is equal to 2. I'm asking a question. Is the information content of the left system of equation equal to the information content on the right-hand side? Okay. According to the definition that we have in our math textbook, two systems of equations are algebraically equivalent whenever they preserve solution. That's what allows us to move terms from the right-hand side to the left-hand side of the equation, add equations, subtract them, multiply them, okay? Because they preserve solution. The solution is preserved here and here. Is the information content the same? I claim no. Anyone claims yes? The algebraic content is preserved, but not what we can do with it. Because on the left, I can ask a counterfactual question, what if I were to hang there 2 kilograms? And I'll get the answer. What if x were 3? I can get the answer. How? I take away the x equal to 1, substitute 3 in here, and I get y is equal to 6. Right? So our first conclusion is that physics equations are non-algebraic. They are counterfactual. That is, they allow you to come up with counterfactual solution, or the solution to a counterfactual query, okay? Whereas algebraic equivalent might not. But how do we get that? In order to get the right result there, I have to go there and wipe out the boundary condition, x equal to 1, and substitute a new value for x. Okay? Wiping out the equation is an operation. Wiping out is an operation which wasn't taught to us in high school physics. You do it in your mind. The teacher changed the conditions, you just substitute x equal to 1. Okay? But if you were to give it to a robot will say, wait a moment, there's contradiction here. You just told me x equal to 1. Now you tell me x equal to 3. Contradiction, I can't solve it. Okay? So you have to equip a robot with the operation of wiping out equations. And that calls for new algebra. Algebra in which one operation is wiping out certain equations, replacing them by others. That's all there is, indeed. From now on, everything follows, and I can quit this stage and let you follow it. Because once we understand what it is to answer counterfactual questions, the rest is pure mechanical or algebra. So if we, the equality sign in the first equation was wrongly assumed to be algebraic. It's not algebraic. In an assignment like in programming languages, you assign to y the value that is obtained from a process by which someone multiplied 2 by x. Good. Or an arrow, and that gives you already a relationship to graphs. And now we go further, and we generalize it. Now we imagine that the whole world is one big collection of springs, and every variable is a function of other variables. So every variable vi is a function of other variables. Some of them are on the boundary. We call them exogenous. Some of them are also product of those functions. And the rest, if you want to play the game of probability, you assign probability to the exogenous variables. And then that induces distributions PV over all the variables, because you have deterministic mapping here, and you're done. What do you mean by done? I mean that you can take, here's an example of a causal model. We're all familiar with it in the Technion. Like a bunch of logic gates. Every variable is a result of a function whose inputs are other variables. Nothing mysterious about it. It's extremely naive and simple. And what you can get by that, I just want to confess here that I'm guilty of the same trauma that I'm witnessing in people who would not listen to me. I mean, people whom I'm trying to convince. In 1988, in my book Probabilistic, I thought that probability is the fundamental representation of human knowledge. I admitted my mistake in a 2000 book, and I said, no, probability is nothing but a surface phenomena of something deeper. And what is there in the deeper is a causal structure. Let's pursue it further. So once we have this picture of the world as a collection of springs, we can define counterfactual precisely, we can axiomatize it, we can find the algebra for counterfactual, and we can answer all questions that one can dream of asking about the behavior of a system. Some of them will be answerable given the knowledge that we have. Some of them will not be answerable. But answering I don't know is also a good answer. It saves you a tremendous amount of computation. You know how many man-hours were saved by the rule that you cannot solve 3 equations with 4 unknowns? Just think about it. It's a good answer. You look at the question, you count, and don't waste your time. And now we have that tool to tell anyone who has a question in probability, in causal intervention, or in counterfactual, whether you have sufficient knowledge to answer the query of your interest. So here we have now, we define a counterfactual. We denote it by y sub x equal to y. Too bad it's faded. It stands for y would be small y in situation u had x been x. What does it mean? It means that in a mutilated model, where I cut off the solution for x and replace it by a constant small x, I'll find the solution y. It's a value that y would obtain in a mutilated system of equations. So now we have a simple algorithm. Give me a system of equations. I take out the equation for x, that's antecedent, replace it by a constant small x, solve for y. That y, that solution, is nothing else but the semantics for the sentence y with for small y. Yeah. Y with a small y had x been x. So we have a semantics for counterfactual. Not the end. For philosophy, it will be the end. But for computer science, you need maximization, you need the algorithm, and all kind of machinery that goes with it. So here's one thing you can do with it. You can find joint probability of counterfactual. Give me any 3 variables, x, y, z, and w. I can find for you the probability that y would be small y had x been small x, and simultaneously, regardless of contradiction, z would be small z had w been small w. Once I have a joint distribution, I'm almighty. Everything follows. I can talk about conditional probability, I can talk about graphoid and conditional independence. All the nice things you have for probability theory, I can do on counterfactual. For instance, I can talk about the probability of y given do x, a special case. I can talk about retrospection. Like, for instance, given that the patient died and he took a drug, what's the probability that he would be alive, y prime, had he not taken the drug? Okay? Cases like that comes in court every day. Is the manufacturer of the drug responsible for the death of the patient? Okay? It's nothing else but a counterfactual sentence with the probability is well defined. And if I have all the functions there, I can just calculate it. Of course, we don't have the functions. And that's exactly where computer science comes into the play. What if you don't have the function? What can you still get out of it with a minimum number of assumptions? Okay. How am I doing on time, Danny? 20 minutes I have? Wow. Now that we have counterfactual at our disposal, we can do miracles. So let's do it together. I'll walk you through a few of the algebraic steps that allows us to conclude the nice things that I'm going to show later on in the application. First, causal Markov theorem. You can prove it in 2 lines. It says that if you have a causal network, namely arranged by cause-effect relationship, where the son is the consequence of the parents, okay, then the probability is decomposable by this product of conditional probability of the son given its parents. Okay. And conclusion is that if you want to find, to answer a manipulation query, like what would be the distribution if I were to manipulate a variable, not to observe a variable, but to do that, okay, the answer is that you take the product. After you mutilate that equation, namely you substitute a constant for the variable that you manipulate. Okay. So you have a truncated product here. For instance, to display to you the case, here we have a collection of variables, seasons, sprinkler, rain. If you ask for the probability that the pavement will be slippery given that the sprinkler is on, you get one result from ordinary conditional probability. But if you ask for the question what the probability is the pavement will be slippery if I were to turn the sprinkler on, I do that, then you cut off this conditional probability between x3 and x1, and you impose your muscles on top of the mechanism that previously decided whether the sprinkler is on and off, and that calls for truncated product, and here you have the correct answer, which is not equal to the conditional probability on the sprinkler on. Good, so we know how to manipulate things. I'll give you quickly the evolution, the historical evolution. The first person who thought about it, about this kind of surgery, was Havelmore, who is the Nobel laureate in economics. In 1943, he came up with the idea that if government wants to impose a certain price on a commodity, right, then you take out the equation of this price and you replace and you balance it with a certain force that keeps it constant. Okay? That was his idea. Other economists talked about wiping out the equation and replacing it by a constant. And then once you have the graphical language to talk about, it amounts to something very simple. You cut off the arrows that goes into the manipulated variables, and correspondingly you cut off the factors that correspond to these arrows. And then it followed by do calculus, where I realized that cutting off equations is an operation that should be treated like a new algebraic operation. So it has its own algebra, its own rules. And then a student of mine, Balki, came up with, let's do it to counterfactual. And he defined it that way, and today it constitutes a unification formalism that embraces the Niemann-Rubin approach and the Lewis possible worlds approach. Let me talk about Lewis for a second, because most people, when they see the word counterfactual, they think about Lewis' book. He's a philosopher, a non-philosopher of science, and he had, well, this is a typical kind of a query or puzzle that philosophers dealt with. Ask 2 questions. If Oswald didn't kill Kennedy, someone else did. Most people said, yes, it makes sense. You know that Kennedy is dead. If Oswald did not kill, then somebody else. Now you go to the subjunctive mood and you say, if Oswald hadn't killed Kennedy, someone else would have. And most people say, I'm not sure. Okay? So most people will say no. Why would anybody kill Kennedy? Even if you are not too familiar with the politics of Texas in 1963, you say it doesn't make sense. But I'm not dealing here now with the politics of Texas in 1963. I'm dealing here with a phenomena which is puzzling, that people form consensus about counterfactuals with the little they know about politics. And that is a puzzle. And the puzzle that should have been really asked 200 years ago when Hume came out with this definition of a cause. This is Hume's definition of a cause. We may define a cause to be an object followed by another, where if the first object had not been, the second never had existed. It's a little convoluted sentence, but look at the urge of Hume to define cause in terms of counterfactual. Look at it. Had not been, had existed. Okay? Why? Are counterfactual less problematic than cause? We communicate with cause and effect. Once I start talking about had not been and had existed, I lose you. Evidently, Hume felt that there is something basic, more basic about counterfactual than in causation. And the same thing with Lewis' definition. A has caused B if B would not have occurred if it were not for A. That's also a little convoluted, despite the fact that we are talking about 1986. But again, it's the urge that counterfactual are more stable. We understand counterfactual more than we understand causes. Okay? And I'm asking, why not define counterfactual in terms of causes, the other way around? Is counterfactual more basic? I say yes. This is Lewis' account of counterfactual in terms of possible worlds. When do I say that B, if it were A, is true? Whenever B is true, in all A worlds which are closest to our world. Okay? That's his picture. And it was enough for Lewis to develop an axiomatic system of counterfactuals. But look, it depends on the idea of closeness. The closest A world to our world. Can you imagine what it takes for a human being to estimate how close is the world in which Oswald refrained from pulling the trigger to the world, to our world in which he did pull the trigger, and make sure that the listener judgment of distance matches the speaker judgment of distance. That's hard to envision. It's more reasonable to assume that we share structure, causal structure, and then the counterfactual is defined by the structure itself, not by degree of closeness. And indeed, one can find a correlate between the two of them. Namely, that the mutilation is an operation that brings you to the closest world. So I am sold about structural counterfactual as opposed to closest kind of counterfactual, similarity-based counterfactual. What do we do with it? First, we can axiomatize it. And these are the 5 axioms that turn out to be sound and complete for the structural counterfactual. From them, everything follows. Okay? Of course, it's hard to work with axioms. You need to have algorithmic. So we go to, this is the working horse. Okay, let me show you now what one can do with the algebra, with the machinery that comes out of all this axiomization and the semantics. Okay? Assuming that you are, say, economist, and you have a collection of equations that tie together economic variables, x, y, z, w1, w2, w3. You don't know the functions. I started by saying if you have the functions, you have everything defined. But you don't know the functions. All you know is the arguments. Who depends on whom? That's how you start your exercise. Okay? If you don't know the functions, then what do you have? Just who depends on whom is a graph. So I would say that this is equivalent to that. There is no more information here than you have here, and vice versa. Because in the graph, I simply display who depends on whom. Who are the arguments in each function? So whatever you can do with the collection of unknown functions, you can do with the graph. What can you do? Here's a linear correlated set. But we don't want to bind ourselves to linear analysis. one thing you can do is ask, what are the testable implications of this collection of functions? Extremely important thing. You have a model, qualitative model. You just know who depends on whom. Does it impose any constraints on the universe that you observe? So what are the testable implications of them? It turns out, you look at the graph, that these separations are the missing edges. Whenever you have missing edges between two variables, then they are separated by some subset of variables. So if you condition on that subset, you get a conditional independence imposition. This is testable. And these are the only testable things for a Markovian graph. So we solve the problem of testability. Solve, I mean, just identify how to test a qualitative model in which you don't have the functions. Okay. What else? I'm going fast here. Okay. If we regress Z1 on all other variables on the model, which regression coefficient will be 0? Why is it important? Because this is how economists test their models. Let's add a regressor to the regression equation and see which coefficient is stable and which is not stable. Because the non-stable ones are something wrong with them. And that's wrong. Because if you look at the graph, you get the answer immediately without even doing the regression. You know precisely who remains stable and who is not. Let me go a little faster and get to the question of, suppose we wish to estimate the causal effect of one variable on another. X on Y. And we are not allowed to conduct experiments. If we had the options, a big grant, of conducting a randomized experiment, then we can just manipulate X and see what happened to Y. But we're not allowed. We have to do observational studies. The theory tells you which variables you should condition on in order that the conditional probability will give you the correct causal effect. It selects for you the right subset of variables according to a certain criteria. If you break all the non-causal path from X to Y, then you are done. So W1 and Z3, the proper admissible. This is also admissible, and other admissible as well. So I'm giving you a flavor for what kind of queries you can answer without doing any analysis, any quantitative analysis, just by looking at the graph. If these are non-observable, they are just hypothesized variables. And all you can observe, W3, you can still get the correct causal effect. So the theory tells you. The theory is now complete, which means we can tell you exactly if you have enough observed variables in your system that will allow you to estimate without bias the desired causal effect. Here's an example of coming from sports medicine. Whether a warm-up exercise is harmful to injury, will increase injury, or will reduce it. That's something that every coach is interested in. And you can see the complexity of things you have to take into account, the type of coach you have, genetics of the players, and so on. Here's a graph. Well, suppose you can measure only a few of the variables here. Which one would you choose to measure in order to come up with the correct, unbiased estimate of the causal effect of warm-up on injury? It turns out this is fine if you can measure Z1 and Z2. It turns out that this is fine. No, don't ever condition on a collider. 5 minutes. Oh, right. So I'll go a little faster. The theory tells you everything without any effort. It all comes out from the theory. That's what I want to say in my last 5 minutes. Computer science is the science of the lazy. We don't want to think. We want a little computer to do the work for us, even for difficult questions like sports medicine. Right? So tell us, computer on the wall, what shall we adjust for to get the right result? This is a good, and that is good. And here are the axioms. by which you can generate every valid sentence, which has a mixture of doing and seeing. The do is in the purple and the seeing is in the white. What does it mean to estimate the causal effect? It means to remove all the do, because you cannot conduct experiments. Okay, so here's an example. I have a graph. What's the effect of smoking on cancer? I want to find the effect of doing smoking on cancer, and unfortunately, I have a purple item there. I cannot conduct experiment, therefore I have to massage it until I reduce it to totally white sentence. If it's totally white, it has no experiments. I can just deduce it by passive observation. Okay? Here are the rules. Chick-chack, you get the right answer. It's doable. If you get stuck, it's undoable because it is complete. It was proven to be complete. Another thing you can do, let me see, I'll skip here. You can find if two models are equivalent. You can find whether you can identify counterfactuals. Mediation, I wouldn't have time to talk about it, but something that I do want to talk about is the external validity, because it's something recent that was done with me and my student Elias, and it's brilliant. You know, I'm very modest, but it gives us such a pleasure to take a problem that was hanging there for centuries, and people talked and talked about it. No one did anything, and reduce it to algebra, because I'm a lazy computer scientist. So here it is. I'll skip through mediation. I'll just tell you, if you have any interest in terms of finding out the right path that nature takes between the aspirin and your headache. And we have today techniques of evaluating hypotheses, namely evaluating the strength of various paths. I'll just go quickly on that. Even mention the beautiful results of here, Arvin, Spitzer, and Pearl. A certain path-specific subgraph that are identifiable and others are not. It's a nice mathematical results, which is becoming very, very popular today with the outburst of work on mediation analysis. But I want to go here to external validity because it demonstrates some. I have 5 minutes to say that I can take from the question answer. So I'm going to steal from you, from your questions. 5 minutes because I want to brag. I really want to brag and to show you the flavor of what you can do with computer science kind of discipline, okay, that solves a problem that social scientists and statisticians and philosophers have dealt with for centuries without any problems. The question is external validity. You conduct a study in a laboratory, and you assume that the results will be applicable outside the laboratory. Without that hypothesis, that things which I observe here will be valid outside, there's no science. They have apples and oranges. There's something which is common to apples and oranges that allows you to infer from the laboratory to the outside. But what have people have done there? They just define what external validity is. Ask the question of generalizability. To what population setting, treatment variable and measurement variable can this effect be generalized? Another kind of expression, experiment is said to have external validity if the distribution of outcome realized by the treatment group is the same the distribution of outcome to be realized in the actual program. Okay? Here you're talking about a policymaker concerned about implementing a certain policy, and somebody did a study. Is it generalizable? And so on and so on. The whole literature, if you look at the literature, is full of threats. Namely, what could go wrong? What could go wrong to defy this desire to generalize? A threat to generalization in making a generalization. And for us, computer scientists, we like to replace threats with assumptions. What should be right? What can we assume to guarantee that all these threats will be neutralized? Okay? So that's what I'm talking about. And I'll show you how it can reduce it to algebra. Assuming, let me go to the example. Okay. Assuming that I conduct an experiment, and I'll go to epidemiology for a second. But you can imagine that you train a robot in a cockpit or in a simulated environment, and the robot goes outside, and then a field environment is different than the simulated environment. Okay? What parts of what the robot learned in the simulated environment are generalizable? And how can the robot change what he or she learned in the simulated environment so as to take into account the differences? This is the question which overrules every scientific inquiry. And now I have the pleasure of showing you how it is reducible to algebra. So we are conducting an experiment about, say, the effect of drug on outcome in Los Angeles for every age group. And then we go to New York City, and we conduct observational study in New York City. We spent already enough money in Los Angeles. We don't have the money to conduct another experiment in New York City. We just look at the telephone book, and we have a passive observation of behavior. Okay? What can be generalized from here to here? For instance, if we measure here the probability, joint distribution of x, y, and z, and the effect of x on y for every age group, that is measured in the controlled experiment in Los Angeles. But now we go to New York City and we measure a different distribution here because people in New York City are a little older. The age distribution there is different. Okay? How can we generalize from here to here? First of all, express it. What do you want to find out? I want to find out the causal effect of x on y, p star in New York City. Okay? This is what I want. It's done because once you express it, it's already in mathematical form. I can master all the machinery. Okay? But how it's done? Okay? First, intuitively, all we need to do is to adjust for the age distribution. Okay? Because we assume that the age-specific causal effect is invariant. Okay? So you and I intuitively will say, yes, we just have to properly adjust for the age distribution. But now notice that it depends on the story. It's not, this kind of calibration is not true for any x, y, and z. It depends where z sits in the causal story. If z was, for instance, if z was not the age, but language skill, then it will have a different answer. For instance, because if children in New York City learn to read at an earlier stage, for some reason, then reading ability has nothing to do with the effect of x and y. So it should be naturalized. So it depends who z is, who the variable is, that accounts for the differences, where it sits in the causal story. I'll cut things quickly and go to the end result. What we want is to have an algebra that given a graph of relationships, and given the area where you suspect that there are differences between the two environments, the environment in which you conducted the experiment, and the environment, the target environment, where you want to apply your results. So here we have two S's, S and S prime. I suspect that the relationship between y and z in the target environment will be different. So I have a marked graph, marked with squares. The squares indicate suspicions of differences. Okay? I get a general graph like this, and what I expect to get is 4 outputs from my bucket calculator. 1, is the causal effect transportable or not? 2, what measurement should I take in each environment in order to be able to transfer knowledge from here to there. 3, this is almost the same. And the third one, what should be the proper combination of those measurements that if I combine through and I massage, will give me the correct answer to my query. This is now doable, and we have a complete theory about it, and here's the answer before. Right here, you can see what the answer is. Thou shalt conduct the green studies in the experimental domain, and the pink one you take by passive observation in the target domain, combine them in this fashion, and you get the right results. So, for the sake of time, I go fast, but you can follow, because it's so simple. Being, I repeat myself, here's a bunch of candidate structure. I don't know ahead of time whether things are transportable or not. I give you the graph decorated with my suspected factors here, with the S. Okay? Which one of them is transportable or not? Computer on the wall, it tells you the green ones are, the purple ones are not transportable. And this is how you combine measurements from a variety of studies under different conditions for different populations.
Excuse me?
Yes?
What if there is another factor, like cultural difference?
If you don't know, if there exist in real life differences, and you don't know about it, then the answer is, I don't know. You can only infer by mathematics results of inputs that you provide. So what we have done is allow you to express mathematically qualitative suspicions that you have about existing differences. If you don't have those suspicions, nothing can be done. The answer is no. Thou shalt not transfer from monkeys to human beings. If you don't know anything about what's common and what is different. Yeah. But if you know that the cardiovascular system is roughly the same, the culture is different, then you can identify it on the graph. That's the game here. I cannot produce knowledge from mathematics. I can only massage knowledge and infer new knowledge that is derivative of the input knowledge. I raise my hand. Any other questions? Okay, conclusions. Counterfactual are the building blocks of scientific thoughts, and on the free will and of moral behavior, because the ability to go back and imagine a new world a new scenario, in which your action would be different, were different. And taking responsibility for those actions is the basis of free will and moral behavior. And the algorithmization of counterfactual brings us a step closer to achieving cooperative behavior among robots and humans. And the third one is, moreover, the algorithmization of counterfactual has benefited several problem areas in the empirical sciences. People who do not care the least about robots. They want to transfer experiments from Los Angeles to New York. They don't care about robots. But again, I'm repeating now the way I started. Our attempt to equip robots with reasoning modes that we find among scientists and human beings enabled us to algorithmize and axiomatize and systematize that process to the benefit of people who cares nothing about robots. I have one more slide. And this is a quote from Einstein saying that development of Western science is based on two great achievements. The invention of the formal logical system in Euclidean geometry by the Greek philosophers. And the second was the discovery of the possibility to find out causal relationship by systematic experiments during the Renaissance. He's talking here about Galileo. And my little contribution there, it says perhaps we are facing another not revolution, but another step forward. Putting the two together and basing causal inference on a formal system that is reducible to algorithmic in the implementation may well be the next development Western science is waiting for. Thank you.